Hi everyone, welcome to part B of our IPKISS and Lumerical series. In this part, we'll be creating a advanced PCell, so it'll be a more complex PCell device, and what we'll want to do here is we'll want to leverage the PCell we made in part A and use it as a building block to create something more complex and also tie a simulation to it. So to start off, the device we'll be making is called the Contra-Directional coupler. In essence, it is just two Bragg straight waveguides brought in close proximity so that coupling can occur. And then the value of this device is that when the signal comes in, there will be a filter response happening, so similar to the Bragg grading. But instead, the filtered signal will cross over to the bus waveguide and exit on the secondary port. So the through port here would keep the original signal with the filtered signal removed, and then the drop port over here will have the filtered out signal. And the value of this device is that this allows the filter signal to not return in the same port as the input. In some cases, for example, if there's a laser, it would maybe get damaged by it. So this kind of alleviates the problem. And it also allows you to have a secondary readout to create different kind of circuits and devices. So this device is pretty much similar to our Bragg straight waveguide in design. The only new parameter we need to be aware of is the gap here. And what we want is to know the location of the next waveguide, because what our plan is to place both devices down and then move the second device up by a certain margin into the location such that it respects our gap parameter. And we'll get to that in a little bit. So to start off, what we'll do is we will first import our libraries. So to do so, we can do from SI fab like before. We'll import all as PDK. And then we'll, from IPKISS 3, import all as I3. Next, what we want to do is we'll do a relative import of devices. And we're going to try to import our Bragg device file over here that's located in the other folder called Bragg straight. So a quick and dirty way to do this is to import the OS and import the system. And then what we'll do is we'll get the current directory, which is os.path.dir_name, and then os.path.realpath, and we'll give it the file, which will be this file. Next, we'll get the parent directory, and we'll need this to locate our other file. So this will be os.path.dir_name again, and we'll call it current. So we'll call the path of the file above. And then what we'll do is we'll append the parent to our system path. And then with that, we'll have access to the designs folder. You can see here that the autocomplete found it. That's a good indicator that our import worked. So designs, and then we'll import our Bragg straight folder. And then from there, we'll import Bragg straight. This is the Python file now. And then we'll call it Bragg, which will be our object. Next, we'll do the same thing as we've done in the previous code structure. So we'll declare our class names and everything. So to start off, we'll do class Contra-DC. And then this will be an I3 PCell like before. And then we'll have our parameters here. So I'm just going to copy over the code we have to save some time on this. And then we'll go over the differences. So the only difference we have with this device is that we have two separate sets of corrugation widths and waveguide widths, and also the gap we mentioned before. The rest of the parameters will be exactly the same. So here we created a separate corrugation width, so corrugation width 1 and 2, and then waveguide width 1 and 2, and then a gap parameter. And then what we can also do is we can go into our Bragg straight script here, and we can copy over the validate properties, just so as an example of using the validate properties if necessary. And pretty much we're good to go on the parameter side. Next, we'll add our class for the layout, and this will be a i3.layout view. And then in it, we'll have our generate elements function. So we'll return nothing for now, just so the function doesn't pop an error. And then we're also going to want to have a generate ports function, so we'll also return. I think we could just have it return the respective lists, so alems and ports. And then finally, we'll add in our script if it's running standalone, so we can test it. So this will be if name equal, and then here we can call our object here. So we'll create an object called device CDC. It will be a Contra-DC object. And then from there, we'll also create a device layout, which will be our device CDC.layout. And then what we'll want to do with that is we'll want it to show, so we'll visualize, and we can have it annotate as well. And then we can also have it output a GDS file. So layout.write _ GDS2. And then we'll call it cdc layout.gds. So this will be show device in console, and then this will be generate GDS. So now what we can do is we can start creating our geometry. So the first thing we'll want to do is we'll also want to create a special custom function, and you can do this however you like. It's very free in IPKISS to do so. It takes after Python. There's not many limitations. So our function here, what we'll do is we'll have it calculate the gap position that we want. So coming back to our diagram here, the device is drawn at a location of x equals 0. So it's around somewhere here on this star. What we want to do is we want to know where this location, where the next waveguide should be. And how we would do that is we know the width here, which is width 1. We know the corrugation width, which is corrugation width 1. We know the gap, and then we also know the corrugation width 2, and we also know the width 2 up here. And that will get us there. And keep in mind the corrugation widths and the regular widths are both divided by 2 because we're only caring about one side of the geometry. We can do a quick calculation here. And this saves problems somewhere down the line. So let's say you're drawing something in generate elements and you need to do this calculation over and over. You can just go to one place to find it. You don't have to keep updating your code or script. So here we'll do a function called calc gap position. How about that? And we'll pass self because it's a self object. And then we'll call the value we want to get bus waveguide y position. And we'll do our calculation here. So we'll do waveguide 1's width divided by 2. And then we'll add half of the corrugation width 1. Then we'll add our gap. Then we'll add the corrugation width 2, also divided by 2. Corrugation width 1 also has to be divided by 2. And then finally, we'll add half of our waveguide 2's width. So self waveguide 2 width divided by 2. And then we'll just have this function return this variable, whatever it's called. And with that, we're good to go. So now we can go into our generate elements here. And let's create our two waveguides. So instead of doing what we did in the Bragg straight here, where we had to create all these rectangles and place them in the right place, we can just reuse our code. And that's where that import we did up here on line 9 comes in very handy. So we have an object called Bragg that we can call. And what we'll do is we'll go down here, and under generate elements, we'll create a new object called Bragg1. So this will be our first straight Bragg grading. And it'll be a Bragg object. And from the Bragg object, we'll call our class Bragg straight. And now this device is initiated. And we'll do the same for our second Bragg. So Bragg 2 is also a Bragg.Bragg straight. And then, of course, we'll want to add these to the element list we have. So we'll just do allems plus equal Bragg 1. And then what you'd want to do is you want to add the layouts elements. So whenever you have a layout class like this, it actually has a bunch of elements that are generated by this generate elements function. And that's what we're kind of pulling from here. We're pulling this layout classes generate elements here. And we're going to add that to the Contra-DC's elements. So we'll also do the same thing for the second Bragg grading. And with this, we will have devices already. And we can give it a quick test just to see. So we should be seeing only one Bragg straight waveguide. And the reasoning is because they're stacked upon each other. They're both at position X and position Y equals 0. We didn't move them. So you can see here, we see one device as anticipated. The colors are actually a bit saturated, kind of indicative of the fact that they're overlapping, but it's not really a consistent way to look at it. So I wouldn't suggest using colors to confirm if something's overlapping or not. But what we'll do next is we'll fix that whole problem. So next I'll show you how to change the parameters for each of these individual objects we created. So it's very simple. We can just call the object itself, and then whatever parameters it has, we can use the dot notation to find them. So in this case, let's say we want to update the corrugation width because the first the first Bragg should have its own corrugation width that's different from the second one. So here we'll do self.dw1, which is the parameter we set in the contra-directional coupler up here for it. And then we'll also want to change the waveguide width. So this will be self.waveguide width 1. We'll also want to update the period and period numbers. So Bragg.period equals self.period. And this is just to make sure it stays in line with whatever we set for the contra-directional coupler. If we don't set it, it'll take the default. Here the default will be 0.32. And then our contra-directional coupler is actually being 0.324. So just this minor difference. And then because the period is changing, we'll want to change the period number as well, just to remind ourselves. So period num. And lastly, we'll also want to disable the cladding. So we'll call the original cladding value and we'll set it to false. So the reason why I disable the cladding here is when we draw this device, it will come with its own cladding by default. By default, it is enabled. So if I remove the fill here and pretend this is the cladding for the box, each device will draw a cladding like so. If we let the claddings remain, we'll get this weird overlap of the two boxes. And sometimes this can cause layout submission issues and you have to go back and change them. So the better way is just to not draw this from the previous function and have this new device function draw it instead. Just one of the possible ways of remedying this problem. So we'll set it to false here, and then we'll copy everything here, and we'll do the same for our second Bragg grading. So Bragg 2, corrugation will be corrugation 2. Bragg 2's waveguide width will be waveguide 2. The period will be updated, and then the cladding will be disabled as well. And then next, if you recall, we also want to place our second device at the new location. So we need to call upon the function we created up here, calculate gap position. So we'll just do Bragg2 dot y position. So if you recall in the previous part, we created a x position and y position just for placing this device. And here's where we're going to use it. So we'll set the y position to our new function, which is called calc gap position. And we don't have to pass it any arguments. It'll return the calculation itself for us. And with that, we can do a quick test to see how it looks. So everything looks good here. Check, and looks good. We have two straight waveguides now with Bragg ratings, and they have their own corrugation width sizes and their own waveguide widths. So it seems like everything is set up correctly. And that'll bring us to the end of this video. In the next video, we'll add in the cladding, and we'll set up the ports. And if we have time, we'll continue on into part of the simulations code. Thanks for watching.